In this video, we're going to go over circular motion. We're going to cover topics like centripetal force, tension, satellite motion, Newton's law of gravitation, so gravity, and things like that. So let's begin. Now let's say if you have a force vector directed to the right and also a velocity vector. What's going to happen if an object is moving to the right and there's a net force acting on it towards the right? Whenever the force and velocity vectors are in the same direction, the object speeds up. The velocity will continue to increase. Now, what's going to happen if the force and velocity vectors, if they're anti-parallel, or if they're in opposite directions? In this case, the object is going to slow down. The speed is going to decrease. Now, what happens if the velocity vector and if the force vector are perpendicular to each other? What is the object going to do? Will it speed up? Will it slow down? Or will the speed remain the same? If the force is perpendicular to the velocity, it has no effect on the speed. The magnitude of the velocity remains the same. However, the direction changes. The object will begin to move in a circle. Whenever the force is perpendicular to the velocity, it acts as a centripetal force. It causes the object to turn. Whenever you have a force that directs an object to turn into a circle, it's called a centripetal force or a center-seeking force. Now at this point, the velocity is directed in the upward direction, but the force is going to be directed towards the center. So the object is going to turn again. It's going to turn in a direction of the force. So it's going to turn towards the left. Now at this point, the velocity vector is directed west, but the centripetal force still points towards the center. So it's going to turn towards the south. And now the velocity vector is directed towards the south, and the centripetal force is directed towards the center, and it's going to turn towards the east. So it's going to move in a circle. So the centripetal force causes an object to move in a circle. Now there's many things that can provide the centripetal force. The centripetal force is caused by something else. For example, let's say if you have a rope and a ball attached to the end of the rope, and if you swing it in a horizontal circle, what provides the centripetal force on the ball? In this case, the centripetal force is provided by tension. Tension is the force that acts through a rope. And so tension is the force that keeps the ball moving in a circle. Now what about the Earth and the Moon? What keeps the Moon in orbit around the Earth? In this case, it's gravity. Gravity provides the centripetal force. Gravity is the force of attraction. The Earth feels a gravitational force from the Moon, and the Moon exerts a gravitational force on the Earth. They both exert a force on each other. They're equal but opposite in direction. So the gravitational force caused by the Earth on the Moon keeps the Moon moving around the Earth. So at this point, the Moon has a velocity that wants to send it out of space, but gravity keeps it in the circle. So now when the Moon is over here, it has a tangential velocity that is directed towards the west. Without gravity, the Moon would basically fly out of orbit. But gravity is a force that's going to cause it to turn. And so it's going to turn towards the south. Now when the Moon is over here, it's going to be moving towards the south, but the gravitational force that the Earth exerts on the Moon will cause it to turn east. So now the moon is over here, moving east. And then the gravitational force is going to cause it to move towards the north. And so this cycle is going to keep repeating itself. And so the moon remains in orbit. So in the case of planetary motion, gravity provides the centripetal force. So gravity caused the moon to orbit the Earth, and it causes the Earth to orbit the sun. Now let's say if we have a road, and let's say there's a car on the road. I'm just going to draw a box to represent the car. So as the car turns, we know there's a centripetal force. Anytime an object turns in a circle, there's always a centripetal force. So what force provides the centripetal force? Whenever you have a car on a road, the friction between the road and the tires, it provides the centripetal force. It allows the car to make that turn. So static friction provides the centripetal force in this situation. The reason why you want to know what provides the centripetal force, because when you're solving a problem, sometimes you can set the centripetal force equal to static friction, sometimes you can set it equal to the gravitational force, or sometimes you can set it equal to tension. So you want to know what provides the centripetal force, because it's going to help you to come up with the right equations to solve a problem, as you'll see later in this video. Now let's say if you have a road and then it curves like this. So you're not turning. Let's say the object is moving straight, but it's not turning in a circle. It's actually going down the circle. In this case, what provides the centripetal force that causes it to turn? So the ball, in this case, or the object, is not turning on its own. Let's say if you're driving a car, you can turn the wheel towards the left. In that case, static friction provides the centripetal force. But if you have an object that simply follows the curvature of the road, what provides the centripetal force in this case? I'll give you a hint. What force does the road or the surface exert on the ball? The road exerts a normal force on the ball. So in this case, as the ball follows the curvature of the road exerts a normal force. The normal force that's exerted on the road is not the same normal force here. The magnitude is different. In this case, the normal force is equal to the weight. But in the case of this section over here, the normal force not only has to support the weight of the ball, but it also has to provide an additional force to cause the object to turn. So the normal force in this situation is greater than the weight force. Not only does it have to support the weight of the ball, but it must also provide the centripetal force to turn the ball into a circle, or to cause it to change its direction. So just understand that the value of the normal force is greater as the ball changes direction in this region compared to this section over here, where it only has to support the weight of the ball. Now another case of a force providing the centripetal force is the magnetic force. Now you may not need to know this for this chapter, but later on, if you take a second course of physics, or if you're in college, if you're taking physics 2, you may need to know this. It has to do with the magnetic force on a moving charge. A magnetic field will exert a magnetic force on a charge if it's moving. If the charge is not moving, the magnetic field exerts no force on it. So let's say if you have a positive charge and it has a velocity vector moving towards the right, and the magnetic field is directed into the page. So in this case, the positive charge will feel a force that is directed upward. So it's going to cause this charge to move into a circle. So in this case, the magnetic force provides the centripetal force on this moving charge. So what is the equation for centripetal force? Centripetal force is equal to mv squared over r. This is the equation that you need to know. Centripetal force is proportional to the mass, is proportional to the square of the velocity, and it's inversely related to the radius of the circle. So if you increase the mass, what's going to happen to the magnitude of the centripetal force? Will it increase or decrease? Because the mass is on top, they're proportional. So if the mass goes up, the centripetal force goes up. But by what factor? If you double the mass, the centripetal force will double. If you triple the mass, the centripetal force will triple. And the way you can figure this out is by plugging the numbers into the equation. Whatever doesn't change, plug in a 1. If it changes, plug in a number that corresponds to that change. So if we double the mass, plug in 2 for m. And if everything else stays the same, plug in 1. So then the force will equal 2, so that means that the force will double in magnitude. If we triple the mass, plug in 3 for m. And everything that stays the same, keep it 1. So the force will triple. So using that same technique, what happens if we increase the speed or the velocity of the object? What's going to happen to the centripetal force? The centripetal force will increase. So if you double the speed, what effect will that have on the centripetal force? So let's plug in 2. 2 squared is equal to 4. So the centripetal force will quadruple. Now what if we triple the speed? So if we plug in 3, 3 squared is 9. So the centripetal force will increase by a factor of 9. If we quadruple the speed, if we multiply by a factor of 4, the centripetal force will increase by 4 squared or 16. Now what about the radius? If we increase the radius, what's going to happen to the centripetal force? So because the radius is on the bottom of the equation, it's inversely related to the centripetal force, meaning that if you increase the radius, the centripetal force will decrease. So if we increase the radius by a factor of 2, how much will the centripetal force decrease by? So if we plug in 1 for everything that stays the same, and plug in 2 for r, the centripetal force will be 1/2 of its original value, which means that it decreases by a factor of 2. Now what if we triple the radius? So in this case, the centripetal force will be 1/3 of its original value, which means that it decreases by a factor of 3. Now what if we cut the distance by 1/2? So if we make the radius smaller, what effect will that have on the centripetal force? So this is 1 over 1/2. 1 divided by 1/2 is equal to 2. So the centripetal force will increase by a factor of 2. Now what if we double the mass, triple the radius, or better yet, let's say if we double the mass, triple the speed, and if we decrease the radius by a factor of 4, what's going to happen to the centripetal force? So let's plug in 2 for m, 3 for v, and 1/4 for r, since we decreased the radius by a factor of 4. So it's 1/4 of its original value. 3 squared is 9 times 2, that's 18. So this is 18 divided by 1/4. 18 divided by 1/4 is equal to 18 times 4. So the centripetal force is 72 times as great. So it increases by a factor of 72. And so that's how you can answer these types of problems. You can take that approach to solve it. Now, whenever there's a force, there is also an acceleration. And according to Newton's second law, net force is equal to mass times acceleration. So the centripetal force is the mass times the centripetal acceleration. So if we divide both sides by m, we could see that the centripetal acceleration is v squared divided by r. Like the centripetal force, the centripetal acceleration always points inward towards the center of the circle. Sometimes you might see that as a test question, so make sure that you are aware of that fact. Now let's say if you have a circle and an object moving in that circle. What is the frequency and the period as it relates to circular motion? The frequency is the number of revolutions that this object makes in 1 second. So let's say if it makes 5 revolutions per second, then the frequency is 5. The period is the time it takes to make 1 revolution. So the period is 1 over f. So frequency is the number of revolutions divided by the time. And so that's going to give you the revolutions per 1 second. The period is the time divided by the number of revolutions. Now, how can we calculate the speed as an object moves in a circle? How can we figure out the speed given the radius of the circle? Now, if the object is moving under constant speed, this equation applies. The distance traveled is equal to the speed multiplied by the time. So the speed is distance divided by time, if you divide both sides by t. Now the distance around a circle is the circumference. And the time that it takes to make 1 revolution around a circle is the period. So the speed of the object is basically equal to 2 pi r divided by t. So that's one equation that you want to know. So sometimes you may need to calculate the centripetal acceleration using period. Centripetal acceleration is v squared divided by r, which is the same as v squared over 1 times 1 over r. And we know that v is equal to 2 pi r divided by the period. So what we could do is replace v with 2 pi r divided by t squared times 1 over r. 2 squared is 4, so we have 4 pi squared r squared over t squared times 1 over r. So one of the r's cancel. So therefore we have the formula for centripetal acceleration. So the centripetal acceleration is also equal to 4 pi squared times r divided by t squared. So if you know the radius of the circle and the time it takes to make 1 revolution, you can use that to calculate the centripetal acceleration. The units for centripetal acceleration is meters per second squared. So if you want to get these units, make sure that the radius is in meters and the period is in seconds. So here's a practice problem that covers all of the equations, or at least most of them, that we've covered at this point. So feel free to pause the video and work out this example. So we have this 2 kilogram ball and it moves in a circle of radius 10. It makes 20 revolutions every 4 seconds. What is the frequency, period, centripetal acceleration, centripetal force, and the speed? So let's say this is the ball and it moves in a circle and the radius of that circle is 10 meters. So let's find the frequency first. So the frequency is the number of revolutions divided by the time. It's the revolutions per 1 second. So there's 20 revolutions in 4 seconds. If we divide it, we'll get 5 revolutions per 1 second. So that's the frequency. That's how many cycles of seconds, how many cycles per second is occurring. So the ball moves 5 times around a circle in 1 second. Now, what is the period? The period is 1 over frequency, or we can say it's the time divided by the number of revolutions. So the time is 4 seconds, and there's 20 revolutions. 4 over 20 is the same as 1 over 5. So it's 1/5 seconds per revolution. So the period is 1 over 5, or 0.2 seconds. Typically, the unit for period is simply seconds, but it's important to understand what it really means. It's 0.2 seconds per 1 revolution. Now that we have the period, what is the centripetal acceleration? So we can use this formula to find the centripetal acceleration. It's 4 pi squared times r divided by t squared. So let's plug in the data that we have. The radius is 10 meters, and the period is 0.2 seconds. And let's not forget to square it. So 4 times pi squared, that's 39.478. And then let's multiply that by 10, which is 394.78 divided by 0.2 squared. So the centripetal acceleration is very large. It's 9,869.6 meters per second squared. So this ball is moving pretty fast. 5 revolutions in 1 second, that in a radius of 10 meters. That's pretty fast. Now, even though this problem is not practical, I just want you to be familiar with the equations and how to use them. Now let's calculate the centripetal force. If you have the centripetal acceleration, the centripetal force is simply the mass times the centripetal acceleration. So it's 2 kilograms times 9,869.6. So this is going to be 19,739 newtons. Now what about the speed? How can we calculate the speed? Now that we have the centripetal acceleration, we could find the speed using this equation. Or we could find the speed using this equation too. So let's use this one, since we already have the radius and the period. The radius is 10 meters, and the period we said was 0.2 seconds. Two divided by 0.2 is 10, times another 10, so this is equal to 100 pi, which is about 314.16 meters per second. So that's how fast it's moving around the circle. No wonder the centripetal acceleration was so high. So here's another problem that you can try. So we have a plane moving at 400 meters per second, and it makes a circular turn of radius 3 kilometers. What is the centripetal acceleration in g's? So let's say if this is the plane, and it makes a turn, and the radius of that turn is 3 kilometers, and it's moving at 400 meters per second. What is the centripetal acceleration? So we can use this equation. AC is equal to v squared divided by r. So the speed is 400 meters per second. Now the radius is in kilometers. We need to convert that to meters. It turns out that 1 kilometer is 1,000 meters. So 3 kilometers is 3,000 meters. The units have to match. If the speed is in meters per second, then you want the radius to be in meters as well. So 400 squared divided by 3,000, that's equal to an acceleration of 53.3 meters per second squared. So that is the centripetal acceleration. Now what is the answer in G's? G, which represents gravitational acceleration, that's 9.8 meters per second. So 1g is 9.8. What is the value of 2g? So 2g's is 2 times 9.8. That represents 19.6 meters per second squared. 3g's is equal to 3 times 9.8, which is 29.4. So how many g's correspond to 53.3? To find out, simply take the acceleration and divide it by 9.8. So the answer is 5.44 g's. Now, if you want to understand why it works that way, you could use the principles of unit conversion. So we have an acceleration of 53.3 meters per second. And we know that 1g is equal to 9.8 meters per second squared. So notice that these units cancel. So by dividing, you're going to get the number of g's. And so that's why it works out this way. So it's 5.44 g's. Let's try this problem. A 2-kilogram ball attached to a rope moves in a horizontal circle of radius 1. Calculate the tension force. So we have a rope, a ball attached to it, and it's going to move in a horizontal circle. The radius is 1. And remember, the tension force provides the centripetal force because the tension force in the rope caused the ball to move in a circle. The tension force is approximately equal to the centripetal force. It's not exactly equal to it, but for the most part, it's approximately equal to it. If the speed is relatively high, the tension force is going to be equal to mv squared over r. So it's going to be 2 kilograms times the speed of 20 divided by the radius, which is 1. 20 squared is 400. 400 times 2 is 800. So the tension force is approximately 800 newtons. Now in actuality, the ball has a weight force, and the tension force is actually at an angle. It may be at a small angle, but it's not purely horizontal. So the tension force has to support the weight force of the ball. Otherwise, it's going to fall down. So the tension force really has an x component and it has a y component. So Ty is equal to mg. So to find the actual tension force, it's the square root of Tx squared plus Ty squared, based on the Pythagorean theorem. So let's calculate Ty first. So Ty, which is mg, that's going to be the mass, which is 2 times 9.8. So Ty is about 19.6 newtons. Tx, notice that it's directed towards the center of the circle. So therefore Tx is equal to the centripetal force, which is mv squared over r, which we already got as 800 newtons. So now we can use this equation to calculate the tension force. So it's going to be the square root of 800 squared plus 19.6 squared, if you want to calculate the exact answer. So the actual tension force is about 800.24, which is approximately equal to 800. Now let's think about what this means. When the speed is very high, the centripetal force, the 800, is significantly larger than the weight force. So therefore, the overall tension force is approximately equal to the centripetal force when the speed is high. But now let's see what the tension force will be when the speed is relatively low. So let's calculate Ty first. So Ty is still mg, which is 2 times 9.8. And so that's still going to be 19.6. So the weight force is not going to change. Tx is going to be different. Tx is equal to the centripetal force, which is mv squared over r. And the mass is still 2, but the speed is now 5. And the radius is still 1. 5 squared is 25, times 2 is 50. So the centripetal force is 50. Now T is going to be the square root of Tx squared plus Ty squared. So that's 50 squared plus 19.6 squared. So this is equal to 53.7, which is significant relative to 50. So at high speeds, the centripetal force is approximately equal to the tension force in a rope. But at low speeds, the tension force is a little bit greater than the centripetal force because you have to take into account the weight force. Now let's think about this conceptually. Imagine if you have a ball attached to a rope in your hand, and if you swing it horizontally at a very high speed, the ball will appear to look like this. It's going to move in a horizontal circle, and the tension or the rope is going to appear very straight. The rope is going to be almost horizontal. Now, if you spin it at a very slow rate, the ball is going to be at an angle relative to the horizontal. So it's going to move like this. So as you can see, at low speed, the vertical component of the tension force is significant relative to the horizontal component. At high speeds, Ty is very small compared to Tx. So T is approximately equal to Tx. But that's what you want to take from this. So if the speed is very high, the tension force is approximately equal to the centripetal force. If it's low, then you have to incorporate Ty when calculating the tension force. Now, how can we calculate the tension force of a ball when it's moving in a vertical circle as opposed to a horizontal circle? How can we calculate it? So let's call this point A, point B, point C, and point D. Now think about it conceptually. Let's say if you have a rope and a ball is attached to it and you're swinging it in a vertical circle. At what point do you think the ball will feel the heaviest? Will it feel heavier at point A, point B, C, or point D? The ball should feel heavy at the bottom, because at the bottom you have to apply more force to lift it up to get to the top. But at the top it's going to feel very light because gravity is going to help you to bring it back down. But at point A, if you want to lift it from point A to point B, not only do you have to support the weight of the ball, but you must also provide the centripetal force to turn it in the upward direction as you move from A to B. So at point A, the ball it's going to feel the heaviest at point A. So therefore, at point A, the tension force is the sum of the centripetal force and the weight force. At point C, it's the lightest. The tension force doesn't have to be that great because gravity also assists in providing the centripetal force. Gravity is going to help you. It's going to help the ball to turn it in a downward direction. Right now, at point C, the ball wants to go towards the left. Gravity is applying a downward force, which is going to assist the ball to go in this direction. As it moves from C to D, it's eventually going to turn towards a downward direction. So the tension force, or the tension in the rope, doesn't have to be that large. The tension is still going to provide a significant portion of the centripetal force at point C, but the weight force is going to help it out. So it feels lighter at point C. So at point C, the tension force is the difference between the centripetal force and the weight force. At point D and point B, the tension force is approximately equal to the centripetal force, which is mv squared over r. A 2-kilogram ball moves in a vertical circle of radius 50 centimeters at a speed of 20 meters per second. Calculate the tension force in the rope attached to the ball at the top, bottom, and in the middle of the circle. So let's start with the top. So when the ball is at the highest position in the circle, the tension force is the difference between the centripetal force, which is mv squared over r, and the weight force, mg. So now that we have the equation, we just simply have to plug in the numbers. So the mass is 2 kilograms, the speed is 20 meters per second, and the radius is in centimeters, but we need to convert that to meters. There's 100 centimeters in 1 meter, so simply divide 50 by 100, and you should get 0.5 meters. Minus the weight force, which is 2 times 9.8. 20 squared is 400 times 2, that's 800 divided by 0.5, so that's 1600. Minus 2 times 9.8, which is about 19.6. So in this case, the tension force is about 1580.4 at the top. Now what about at the bottom of the circle? At the bottom, the tension force is the sum of the centripetal force and the weight force. We know the centripetal force is 1600, the weight force is 19.6. So at the bottom, the tension force is going to be a little bit heavier. It's going to be 19.6 newtons. Now what about at the side? Let's say if it's moving in this direction. What's the tension force that acts on the rope? In this case, the tension force is approximately equal to the centripetal force at the side. So it's just going to be about 1600 newtons. And so that's all you need to know for the problem where it moves in a vertical circle. A 0.2 kilogram ball attached to a 1.5 meter string moves in the vertical circle. What is the minimum speed that the ball must have at the top so that it continues to move in a circle? So at the top, if the ball is moving fast enough, it's going to move in a nice circle, and the rope is going to be fully extended because there's going to be a tension force. Now, if it's moving too slow, what's going to happen is it's going to fall down, and the rope, it won't be fully extended because there's no tension force, and so it won't be straight. We want to find the minimum speed such that it moves in a perfect circle. And there has to be a tension force for it to move in a perfect circle. So the minimum speed, the threshold, occurs when the tension force is just above 0. So we're going to set the tension force equal to 0. At the top, the tension force is the difference between the centripetal force and the weight force, mg. So if we set it equal to 0 and add mg to both sides, we can see that the centripetal force must balance the weight force. It must be just above the weight force for the rope to remain straight, and so that the ball can move in a perfect vertical circle at the top. Now we don't need the mass, so we can divide by m. So v squared over r is equal to g. And if we multiply both sides by r, we'll see that v squared is equal to rg. So therefore, the minimum speed that the ball requires so that it continues to move in a circle at the top is the square root of the radius times the gravitational acceleration. So it's the square root of 1.5 times 9.8. And the answer is 3.83 meters per second. Go ahead and try this problem. A 0.25 kilogram tetherball is tied to a pole with a 0.75 meter string. Calculate the tension force in the string if the ball makes 10 horizontal revolutions in 5 seconds. So let's draw the pole. This is going to be the string, and here's the ball. So it moves in a horizontal circle. So this is the radius of the circle. Let's call it r. This is the length of the string. We'll call it L. And the time it takes to make one revolution is the period, which we'll call capital T. So let's call the tension force Ft. Let's not confuse it with T. So the tension force has a vertical component. Let's draw the free body diagram. So this is the tension force. This is the vertical component of the tension force. We'll call it Fty. And it has a horizontal component, Ftx. And there's also the weight force acting on the ball. So first, let's find a relation between the length of the string and the radius of the circle. Let's call this angle beta. Now, based on SOHCAHTOA, we can see that sine beta is equal to the opposite side. Opposite to beta is the radius divided by the hypotenuse, which is the length of the string. So solving for r, the radius is equal to the length of the string times sine beta. Now, we can draw a second triangle. Notice that the tension force is related to Ftx using beta as well. So sine beta is equal to the opposite side, which is Ftx, divided by the hypotenuse, which is Ft. So if we multiply both sides by Ft, we can see that Ft sine beta is equal to Ftx. Now Ftx points towards the center of the circle. So therefore Ftx provides the centripetal force. So let's make some space. So we can say Ftx is equal to Fc. And Ftx is equal to the tension force times sine beta. And the centripetal force is mass times the centripetal acceleration. And the centripetal acceleration, we can make it equal to v squared over r, but we don't want to use that equation. We want to relate the centripetal acceleration to the period, because we can calculate the period from the number of revolutions per second. The other equation for the centripetal acceleration is 4 pi squared times the radius of the circle divided by the period squared. This is the one we want to use. So now we can replace the radius with L sine beta. Now the last thing that we need to do is we need to divide both sides by sine beta. So these two will cancel. So now we have the tension force in terms of the period. So it's the mass times 4 pi squared times the length divided by the period squared. So let's calculate the period. The period is the time it takes to make one revolution. So if we take the time and divide it by the number of revolutions, we can get the period. So if 10 revolutions occurs in 5 seconds, then 0.5 revolutions, 1 revolution occurs in 0.5 seconds. So it's 0.5 seconds per 1 revolution. So that's the period. That's the time it takes to make 1 revolution. So now that we have T, let's calculate the tension force. So it's going to be 4 pi squared times the mass, which is 0.25 kilograms, times the length of the string, which is 0.75 meters, divided by the period, which is 0.5 seconds squared. So you should get a tension force of 29.6 newtons. So this is the answer. Alright, let's try this problem. A car makes a circular turn of radius 20 meters. The coefficient of static friction between the tires and the road is 0.60. What is the maximum speed at which the car can safely make the turn without sliding? So let's draw a picture. So here's the road, and I'm going to use a box to represent the car, and the car is turning. As it turns, you need to realize that static friction provides the centripetal force. Static friction between the tires and the road allows the car to turn. And any force that causes an object to turn in a circular direction provides the centripetal force. Now, if the car is moving too fast, static friction won't be able to make the complete turn. It's not strong enough to cause the car to turn if the car is moving too fast. The faster the car is moving, or if it's moving at a higher speed, you need a greater frictional force to keep it or to cause it to turn in a circle. And static friction has its limits. So if the car is moving too fast, instead of turning, it could slide off the road. To solve this problem, since static friction provides the centripetal force, you want to set these two forces equal to each other. Static friction is equal to mu s, which is the coefficient of static friction, times the normal force. The centripetal force is mv squared over r. And in this problem, we don't have a bank curve. It's a level road. The car is simply making a turn on a flat surface. The normal force for a flat surface is mg. So notice that we can cancel the mass, so we don't need the mass. So mu s g is equal to v squared over r. So what we want to do at this point is multiply both sides by r. So these units cancel. So now we have mu s times g times r, and this is equal to v squared. So now we need to take the square root of both sides. So the maximum speed at which the car can make the turn is equal to the square root of the coefficient of static friction times gravitational acceleration times the radius of the turn. In this case, the radius is about 20 meters. So now we just got to plug in everything into the equation and we'll get the answer. So it's going to be 0.60 times 9.8 times the radius of 20. And then we'll take the square root of that result. So for this problem, the maximum speed is about 10.84 meters per second. If the car is moving faster than this speed, if it's making a turn of radius 20 meters, it will skid, or it could slide off the road. A car makes a circular turn of radius 15 meters at 40 meters per second. At what angle should the road be banked so that no friction is required? So let's draw a picture. So let's say this is the car. It has a normal force, and it has a weight force, mg. And let's say this is the angle of the road. Now the normal force has a horizontal component that provides the centripetal force, and it also has a vertical component that supports the weight force. So the angle theta is equal to this angle. So this side is the normal force times cosine theta. That supports the weight force. And on this side, we have the normal force times sine theta. Now, if you want to see why that's the case, let's prove why these angles are equal to each other first. Because some of you out there are probably wondering why those two angles are equal to each other. So let's say this angle is 30. That means this angle is 60, which means that this angle here is 30, which means that this is 60, because this is a right angle. The normal force is always perpendicular to the surface. And if that's 60, this is 30. So therefore, we could say this is theta. So let's prove why this is Fn sine theta and this is Fn cosine theta. So here's the normal force. It has a vertical component and a horizontal component. And here's theta. So let's say this is, let's call this side x and let's call this side y. Cosine theta, according to SOHCAHTOA, is equal to the adjacent side divided by the hypotenuse. The adjacent side is the side next to the angle, which is y. The hypotenuse is the side across the 90-degree angle, or across the box, and that's the normal force. So if you solve for y, you need to multiply both sides by the normal force. So as you can see, y is equal to Fn cosine theta. So this is equal to Fn cosine theta. Now what about the other side? Let's do the same thing. So we're going to have to use sine instead of cosine. So according to SOHCAHTOA, which is SOHCAHTOA, sine is opposite over the hypotenuse. So sine theta is equal to the opposite side, which is x, divided by the hypotenuse, which is the normal force. So if we multiply both sides by the normal force, we can see that the normal force times sine theta is equal to the horizontal side, which we have here. So now you know where those equations come from, just in case you had any doubt. So what you need to know is that this component of the normal force supports the entire weight of the object. So mg is equal to Fn cosine theta. Therefore, the normal force for this type of problem is mg divided by cosine. Now, the horizontal component provides the centripetal force because the car is making a turn on a bank road. So, on a bank surface, depending on the angle, a car can make the turn without the help of friction, because the normal force can provide the centripetal force, or at least the component of a normal force can provide the centripetal force required to make the turn. So we're going to set Fc equal to Fn sine theta. So mv squared over r is equal to the normal force times sine theta. So now somehow we got to find the angle at which the road should be banked, so that no friction is required to make this turn. So we can't use this equation because we don't know the mass, or at least we can't use it in that form right now. Nor can we use this one either because we don't have m. So what we need to do is replace the normal force with mg over cosine theta. So mv squared over r is equal to mg over cosine theta times the sine theta. So if we divide both sides by m, we can get rid of it. So it's v squared over r, and sine divided by cosine is tangent. So now let's multiply both sides by r. So v squared is equal to r. Actually, I'm forgetting something, and that's g. So this is tangent times g. So what I want to do actually at this point is divide both sides by g. Dividing both sides by g is the same as multiplying by 1 over g. So these two cancel. So v squared over rg is equal to tangent theta. So therefore, if we take the inverse tangent of both sides, theta is equal to the inverse tangent v squared over rg. This is the equation that you want to find the angle at which the road should be banked, so that no friction is required to make the turn. So now all we need to do is plug in the information to get the angle. So theta is equal to the inverse tangent v squared, which is 40 squared, divided by the radius of 50 times 9.8. So the angle is 72.97 degrees. Let's try this problem. A car accelerates from rest at a uniform rate to 40 meters per second in 8 seconds on a circular track of radius 600 meters. What is the magnitude of the tangential acceleration, the radial acceleration, and the net acceleration of the car? So let's say if we have an object moving in a circle. Now, if it's turning, it has a radial or a centripetal acceleration. And if it's speeding up as it moves around a circle, it has a tangential acceleration. Now, if you combine these two vectors, let's say this is the tangential acceleration, and this is the centripetal acceleration, then the hypotenuse represents the net acceleration. Whenever you wish to add two vectors that are perpendicular to each other, you can use the Pythagorean theorem. So the net acceleration is equal to the square root of the centripetal acceleration squared, which is the radial acceleration, plus the square of the tangential acceleration. So first, let's calculate the tangential acceleration. The equation that we can use to get it is this equation. V final equals V initial plus AT. So the initial speed is 0 because the car accelerates from rest. We're looking for the acceleration. The time is 8 seconds and the final speed is 40. So 40 divided by 8 is 5. So this is the tangential acceleration. Now let's calculate the radial acceleration or the centripetal acceleration when the speed is 40. So let's use this equation. So when the speed is 40, the centripetal acceleration is 2.67 meters per second squared. So now we could find the net acceleration. So it's going to be the square root of 2.67 squared plus 5 squared. So the net acceleration is about 5.67 meters per second squared. So that's what you can do to find the net acceleration if the object is speeding up while traveling in a circle. A 1,000-kilogram car travels on the road at a speed of 20 meters per second. Calculate the normal force exerted by the road at points A and B if the radius of curvature is 100 meters. Okay, so let's begin. So while the car is moving at point A, the normal force has to apply a force to change the direction of the car. Notice that the normal force points towards the center of this circle. So in that case, the normal force provides the centripetal force. But not only does it provide the centripetal force, it must also support the weight of the car. So it has to work harder in that case. So at the bottom, the car is going to feel heavier because the normal force has to support the weight of the car and it has to change the direction of the car. So it has to provide the centripetal force. So at point A, the normal force is the sum of the weight force and the centripetal force. At point B, the normal force doesn't have to apply a force to cause the car to go this way. As it moves, it's simply going to fall in that direction if it's not moving too fast. So in this case, the normal force is the difference between the weight force and the centripetal force. If it's not moving at all, then the normal force supports the weight force. It's going to be equal to the weight force. But if it is moving, gravity is going to assist it in falling down. So at the top, the normal force is the difference between the weight force and the centripetal force. Those are the two equations that you need to know for this situation. So let's calculate the normal force at point A and at point B. For those of you who want to see the free body diagram, the weight force is directed downward and the centripetal force is directed upward towards the center of the circle. For this one, the normal force is directed upward, the weight force is directed downward, and the centripetal force is also directed downward towards the center of the circle. Just in case if you want to see the free body diagram in action. So for point A, the normal force is going to be equal to the mass, which is 1,000, times gravity, which is 9.8, plus mv squared over r, which is 1,000, times the speed, which is 20 squared, divided by the radius of 100. So the weight force is 9,800, and its centripetal force is going to be 20 squared, which is 400, times 1,000 divided by 100, which is 4,000. So the normal force at point A is the sum of 9,800 and 4,000. So that's going to be equal to 13,800 newtons. Now at point B is the difference between those two numbers. It's the weight force, which is 9,800, minus the centripetal force, which is 4,000. So that would give you a normal force of 5,800. Now, how can we answer the last part? What is the maximum speed that the car can travel at point B without losing contact with the road? So once it loses contact with the road, there's no more normal force. Normal force is a contact force. If the road is not in contact with the car, the road cannot exert a normal force on the car. So to find the maximum speed, we need to set the normal force equal to 0, and that's at the top. So mg minus mv squared over r must equal to 0. So if we add mv squared over r to both sides, you can see that mg is equal to mv squared over r. And if we divide by m, we get this equation. So g is equal to v squared over r. So now let's multiply both sides by r. So these cancel. So rg is equal to v squared. Now let's take the square root of both sides. So the velocity is going to be the square root of rg. So this equation gives us the maximum speed at which the car can travel at point B without losing contact with the road. If the speed exceeds this value, it's going to fly off the road. So let's see what that speed is. The radius is 100. Gravitational acceleration is 9.8. So 100 times 9.8 is 980, and the square root of 980 is 31.3 meters per second. Now let's try another problem. At what minimum speed should a roller coaster be traveling when upside down at the top of a circle of radius 15 meters if the passengers are not to fall out? So let's say if we have a circle. Now the normal force at the bottom of the circle, as you mentioned before, is going to be the sum of the weight force and the centripetal force. But the normal force at the top is the difference between the centripetal force and the weight force. This time, it's going to be in the reverse order. In the other example, the car was above the road. It was basically above the circle. But in this example, the roller coaster is below the circle. And so if it's moving fast enough, the curvature of the tracks will provide the centripetal force, causing the roller coaster to turn. If it's moving too slow, then gravity wins and the passengers will just fall down. So imagine if you have a ball and if you roll it. If the ball moves too slow, it's just going to fall down. But if it moves fast enough, it's going to round the circle and exit the circle. So there's a minimum speed in which any object moving in this vertical circle will maintain contact with the upper part of the circle, and it will not fall straight down. How can we calculate that minimum speed in which the roller coaster won't lose contact with the tracks and the passengers will not fall out? The threshold is when the normal force is 0. If the roller coaster is moving fast enough, the centripetal force will exceed the weight force. So let's say if the centripetal force is 1,000 and the weight force is 700. That means there's a normal force of 300. That means that the tracks is exerting a force on the roller coaster, so it's that means the roller coaster is still in contact with the tracks. But if the weight force exceeds the centripetal force, that would indicate a negative value, which means that the roller coaster is no longer in contact with the normal force, because the normal force can't be negative. So to find the minimum speed, let's set the normal force equal to 0, and let's solve for r. I mean, not for r, but for v. So let's add mg to both sides. So mg is equal to mv squared over r. So we can cancel m, and if we multiply both sides by r, we'll get the equation that we had in the last example. So the minimum speed is simply the square root of the radius times the gravitational acceleration. In this example, the radius is 15, g is still 9.8. And the minimum speed is 12.1 meters per second. Now let's move on to another topic. Let's talk about gravity. Gravity is a force that brings matter together. Let's say this is the sun and this is the earth. Gravity is a force of attraction, and the gravitational force is significant between very large planetary objects. So the sun exerts a gravitational force on the earth, and the earth exerts a gravitational pull on the sun. Now, how can we quantify this force of gravity? The equation that we need is this one. F is equals to g times m1 times m2 divided by r squared. So g is the gravitational constant. It's equal to 6.67 times 10 to the minus 11. M1 and M2 represents the mass of the two objects, in this case the mass of the sun and the mass of the earth, and R is the distance between the center of the sun and the center of the earth. The mass of the sun is about 2 times 10 to the 30 kilograms. The mass of the earth is about 5.98 times 10 to the 24 kilograms. And the distance between them is about 1.5 times 10 to the 11 meters. Using this information, go ahead and calculate the gravitational force between the earth and the sun. So all we got to do is plug in these numbers. So we have g, we have the mass of the sun, that's 2 times 10 to the 30, and the mass of the earth divided by the distance between them. And don't forget to square it. Now let's type this in. So you should get a force of about 3.55 times 10 to the 22 newtons. So that's the gravitational force between the earth and the sun. Now let's say if the mass of the earth was doubled. What effect will that have on the gravitational force between the earth and the sun? If you double the mass of the earth, the gravitational force will increase. If you triple the mass of the sun, the gravitational force will triple as well. Now what happens if you double the distance between the earth and the sun? Will the gravitational force increase or decrease? If you increase the distance, it will decrease. If you double the distance, it will decrease by a factor of 4, or it's going to be 1/4 of its original value. Now what if you triple the distance? Remember, to answer these questions, plug in the 1 for everything that stays the same. If we triple the distance, it's 3 squared, which is 9, or 1/9. So the gravitational force will be 1/9 of its original value, or it's going to decrease by a factor of 9. Now let's say if you triple the mass of the Earth, quadruple the mass of the Sun, and decrease the distance by a half. What effect will it have on the gravitational force between the Sun and the Earth? So 3 times 4 is 12. 1 squared is 1, 2 squared is 4. 12 divided by 1/4 is 48. So in this case, the gravitational force will be 48 times as great. So if you decrease the distance between the two large objects, the force will increase. So if you decrease the distance by a third, 1 over 1 over 9, that's 9. The force will increase by a factor of 9. So if you wish to increase the gravitational force, you can either increase the masses of the objects or decrease the distance between them. The mass of the Earth and Moon are the numbers given. We also have the radius of the Earth and Moon. Using this information, go ahead and calculate the acceleration due to gravity at the surface of the Earth and the Moon. So first, we need to come up with an equation. Now, the force of gravity is equal to the weight force, because the weight force is based on gravitational acceleration. So let's say F is the force of gravity between, let's say, a person standing on Earth's surface and the Earth itself. So that basically is the weight force. And the gravitational force is G m1 m2 divided by r squared. Whereas the weight force of a person is simply mg. So if you cancel one of the masses, in this case the mass of the person, you can get the gravitational acceleration of the planet. So it's g times the mass of the planet divided by r squared. This is the equation you want to use. So the gravitational acceleration of the Earth, which we know to be 9.8, we can calculate it using this equation. So it's g times the mass of the Earth divided by the radius of the Earth squared. So g is 6.67 times 10 to the minus 11. The mass of the Earth is 5.98 times 10 to the 24 kilograms. And the radius of the Earth is 6.38 times 10 to the 6 meters. And let's square it. So using this information, you should get 9.799, which is approximately 9.8 meters per second squared. So that's the gravitational acceleration of the Earth. Now go ahead and use the same equation to calculate the gravitational acceleration of the Moon. So it's going to be gm over r squared again. So g is going to be the same. The mass of the Moon is much less than the mass of the Earth, so we should expect that the gravitational acceleration should be weaker. Now the radius is also smaller though. As the mass of the planet increases, the gravitational acceleration increases. As the radius of a planet increases, the gravitational acceleration decreases. So the gravitational acceleration is directly proportional to the mass of the planet, but it's inversely related to the square of the radius. So let's see what the answer is going to be. So you should get a gravitational acceleration of about 1.62 meters per second squared. So that's the gravitational acceleration on the Moon. It's much weaker than that of the Earth. So if you're on the Moon, you'll feel a lot lighter, so you could jump higher. Now what about the gravitational acceleration 4,000 kilometers above Earth's surface? Feel free to pause the video and work on that example. So let's say this is the Earth. We know the radius of the Earth. The radius of the Earth is 6.38. Okay, let's write that better. Times 10 to the 6 meters. Now, we want to find the gravitational acceleration at a point 4,000 kilometers above the surface of the Earth. So the R value in the equation is the sum of the radius and the altitude of 4,000 kilometers. Now we can't simply add the radius of the Earth and the 4,000 kilometers because the units doesn't match up. The radius is in meters and the altitude is in kilometers. So let's convert kilometers to meters. 1 kilometer is about 1,000 meters. So 4,000 times 1,000 is 4 million, which is about 4 times 10 to the 6 meters. So if we take the altitude and add it to 6.38 times 10 to the 6, this will give us 10.38 times 10 to the 6 meters, which is the same as 1.038 times 10 to the 7 meters. So this is the R value that we want to use. So as you move away from Earth's surface, the gravitational acceleration will decrease. But let's see how much. Let's go ahead and get the answer. So G is going to be the same. The mass of the Earth is still 5.98 times 10 to the 24. But now R is a different value. It's 1.038 times 10 to the 7. And let's not forget to square it. So we should expect an answer that's much less than 9.8. So the answer that I got is a gravitational acceleration of 3.7 meters per second squared. So that's the gravitational acceleration 4,000 kilometers above Earth's surface. Calculate the gravitational acceleration of a planet that has a mass 2 times that of Earth. So the gravitational acceleration of the Earth, we know it's 9.8. And the equation for gravitational acceleration is the gravitational constant times the mass of the planet divided by r squared. So if we double the mass, what's the effect on the gravitational acceleration? If we plug in 2 for m and 1 for everything else, we get a value of 2. So doubling the mass will double the gravitational acceleration. So for part A, the gravitational acceleration of, let's say, planet X is twice the value of that of Earth, so it's going to be 19.6. And it's meters per second squared. Now what if the radius was increased by a factor of 3? So if the planet had a radius that was 3 times greater than that of Earth, what is the gravitational acceleration? So what is the effect of tripling the radius? So it's going to be 1 over 3 squared, which is 1 over 9. So it's going to decrease by a factor of 9. So it's going to be 9.8 divided by 9. So the gravitational acceleration is now 1.09 meters per second squared. Now what if we reduce the distance or the radius of this planet by half? So if we plug in 1/2 into the equation, it's 1 over 1/4, which is equal to 4. So it's going to be 4 times as great. So it's going to be 9.8 times 4, and the gravitational acceleration will be 39.2 meters per second squared. So as you can see, if you increase the mass, the gravitational acceleration will increase. If you decrease the radius, it will increase as well. But if you increase the radius of the planet, the gravitational acceleration will decrease. Calculate the speed and period of a satellite 3,000 kilometers above Earth's surface. So let's say this is the Earth. And here's the satellite. The satellite is in free fall with the Earth. Earth exerts a gravitational force on the satellite, so the satellite is falling towards the Earth. However, the satellite does have a tangential velocity. And as you've learned earlier in this video, when the velocity and force vectors are perpendicular to each other, the object turns. And the satellite can maintain its orbit if it has the right speed. If it's moving too fast, it can escape Earth's gravity. If it's moving too slow, it could eventually fall into the surface of the Earth. But if it has the right speed, it can maintain its orbit. So how can we calculate the speed of the satellite if we have the height? So let's say it's 3,000 kilometers above the surface of the Earth. What can we do? So you need to understand that Earth exerts a force of gravity on the satellite. And because that gravitational force keeps the satellite moving in a circle, gravity provides the centripetal force. So that tells us that we need to set the gravitational force equal to the centripetal force. Now we know the gravitational force is going to be the gravitational constant times the mass of the satellite times the mass of the Earth divided by the radius squared. Now the centripetal force is equal to mv squared over r. Since the satellite is the one that's moving in a circle around the Earth, the mass in the centripetal force is going to be the mass of the satellite times v squared over r. So we can cancel the mass of the satellite and we can cancel one of the r's. So we can see that the gravitational constant times the mass of the Earth divided by the distance between the center of the satellite and the center of the Earth, that's going to equal the square of the velocity of the satellite. So what we need to do is take the square root of both sides. So now we have the speed of a satellite in orbit above the Earth. It's equal to the square root of the gravitational constant times the mass of the Earth divided by the distance between the two objects. So we know the value of g, that's 6.67 times 10 to the minus 11. And from the other problems, we know that the mass of the Earth is about 5.98 times 10 to the 24. Now 1 kilometer is 1,000 meters, and 1,000 is basically 10 to the third. So that's the altitude. 3,000 times 1,000 is 3 million, which is 3 times 10 to the 6 meters. Now the radius of the Earth is 6.38 times 10 to the 6 meters. And we have an altitude, that's the distance between the satellite and Earth's surface, is 3,000 kilometers above Earth's surface, so that's 3 times 10 to the 6 meters. To get the distance between the satellite and the surface, or rather the center of the Earth, we need to add these two values. So 3 plus 6.38, that's going to be 9.38 times 10 to the 6. So let's see what the answer is going to be. So I got a speed of 6,521 meters per second. That's how fast the satellite is moving at this orbit. Now the next thing that we need to do is calculate the period of the satellite. We need to find the time it takes for it to make one revolution around the Earth. So we know that the speed is equal to the circumference divided by the time, which is the period. You've seen this equation earlier in the video. So what we can do is we can multiply both sides by t, and that's going to give us vt is equal to 2 pi r. And if we divide both sides by the velocity, we can see that the period is equal to 2 pi times the orbital radius relative to the center of the Earth divided by the speed. So we know what r is. We know it's 9.38 times 10 to the 6. So that's the altitude plus the radius of the Earth divided by the speed of the satellite, which is 6,521 meters per second. So the period of the satellite is 9,037.9 seconds. So if we want to convert that to hours, we know that there's 60 seconds in a minute and 60 minutes in an hour. So we need to divide 9,037.9 by 3,600. And so the period of the satellite is about 2.51 hours. So that's how long it's going to take to make one revolution around the Earth. The distance between the Earth and the Sun is 1.5 times 10 to the 11 meters. And I forgot to put the unit there. Use this information to calculate the mass of the Sun. So, if that's all we have, how can we find the mass of the Sun? Now we know it's about 2 times 10 to the 30 kilograms. But what equations can we use to find it? So let's see what the situation is. So let's say this is the Sun, and we have the Earth revolving around it. So the Earth behaves as a satellite around the Sun. And the Sun exerts a gravitational force on the Earth. And that gravitational force on the Earth provides the centripetal force that keeps the Earth in orbit around the Sun. So knowing that, we could set the gravitational force equal to the centripetal force. The gravitational force between two objects, it's Gm, so that's the mass of the Sun, times the mass of the Earth, divided by the distance between them, which is 1.5 times 10 to the 11 meters. The centripetal force is the mass of the object moving in a circle, in this case that's the mass of the Earth, times the centripetal acceleration, AC. Now we could use mv squared over r, but that's going to give us the speed of the satellite, which if we want to find the speed of the Earth around the Sun, we could if we want to, but we're not going to do that. So centripetal acceleration, we can replace it with v squared over r, or we could replace it with 4 pi squared r over t squared, which we obtained this equation earlier in the video. So let's use that for the centripetal acceleration. So it's 4 pi squared r divided by t squared. So we can cancel the mass of the Earth. Let's multiply both sides by r squared over g. If we do that, on the left side, g will cancel and r squared will cancel. So on the left we have the mass of the Sun, which is equal to 4 pi squared times r cubed divided by gt squared. So now let's plug in the information that we have. So r is 1.5 times 10 to the 11. That's the distance between the Earth and the Sun. G is the gravitational constant. And what's t? So t is the period, which is the time it takes for the Earth to make one revolution around the Sun. And we know that's equal to 1 year. It takes 1 year for the Earth to travel around the Sun. But we need to plug the the period using seconds. So we can't just plug in 1 year. Let's convert this to seconds. So we know that there's 365 days in a single year, and there's 24 hours in a single day, and there's 60 minutes in a single hour, and there's 60 seconds in a minute. So it's going to be 365 times 24 times 60 times 60, which is a large number. So it's going to be 315,36000. So basically that's 31,536,000 seconds. Well, let's not forget to raise r to the third power. So now let's plug this information in. Let's see what the mass of the sun is going to be. Also, let's not forget to square the period. So you should get 2.01 times 10 to the 30 kilograms, which is approximately the mass of the sun. By the way, if you're not getting the answer, try typing this information on the bottom using parentheses. Enclose the whole thing in parentheses. Because depending on your calculator, sometimes, based on the way you type it in, the calculator might be dividing by this number and then multiplying by the second number. To avoid that, just enclose everything in the bottom using parentheses and you shouldn't have that problem. Here's another problem for you. Calculate the speed and height above the Earth's surface of a geosynchronous satellite. A geosynchronous satellite is one that stays above the same point on the equator of the Earth. So the period of this satellite is approximately 1 day, because it takes 1 day for the Earth to rotate around its own axis. So all we have is the period. How can we find the height and the speed? So using the equation that we had before, we set the centripetal force equal to the gravitational force. So here we have the gravitational force between the satellite and the Earth, and r represents the distance between the center of the satellite and the center of the Earth. Now, let's say this is the Earth. The satellite revolves around the Earth. So therefore, the centripetal force acts on the satellite because the satellite is moving in a circle. So the mass is going to be the mass of the satellite in the centripetal force equation. Now we're going to replace the centripetal acceleration with 4 pi squared r over t squared. So just like before, we can cancel the mass of the satellite instead of the mass of the Earth. Okay, looking at the last problem. So our goal is to solve for r. So if we cross multiply, 4 pi squared r times r squared is 4 pi squared r cubed, and gm times t squared is g times the mass of the Earth times the period squared. So now let's divide by 4 pi squared. So the distance between the Earth and the satellite, which is r, can be found using this equation. What we need to do now is take the cube root of both sides. So r is going to be equal to the cube root of g, which is 6.67 times 10 to the minus 11. Let's get rid of this. Times the mass of the Earth, which is 5.98 times 10 to the 24 times the period divided by 4 pi squared. So what is the period in seconds? So we know the period of the satellite is 1 day, and there's 24 hours in a day, and there's 3,600 seconds in an hour, because it's going to be 60 minutes per hour, 60 seconds per minute. 60 times 60 is 3,600. So 24 times 3,600 gives us a period of 86,400 seconds. And let's not forget to square the period. So let's plug everything in. So you should get an R value of 42,250,474, which is about 4.225 times 10 to the 7 meters. Now you need to understand that this R value is the distance between the center of the Earth and the satellite. So if we want to find the height above the surface of the Earth, we need to subtract the total distance by the radius of the Earth. So the height is going to be 4.225 times 10 to the 7 minus the radius of the Earth, which is 6.38 times 10 to the 6 meters. So the height is about 3.587 times 10 to the 7 meters. If we divide it by 1,000, we can get the height in kilometers, which is about 35,870 kilometers. So that's the height of a geosynchronous satellite above Earth's surface. So now let's calculate the speed of the satellite, now that we have the height above the surface of the Earth. So the speed of the satellite is going to be the gravitational constant times the mass of the Earth divided by the distance between the satellite and the Earth, which is this number. So it's going to be g, which is 6.67 times 10 to the minus 11 times the mass of the Earth, which is 5.98 times 10 to the 24 divided by the distance between them, which is 4.225 times 10 to the 7 meters. So you should get a speed of about 3,072.6 meters per second. So that's the speed of a geosynchronous satellite in orbit. The distance between Earth and the Sun is 1.5 times 10 to the 11 meters. So let's say this is the Sun. And let's say this is planet Earth. And Earth can revolve around the Sun. The distance between the Sun and Mars is 2.28 times 10 to the 11 meters. So let's say Mars is somewhere over here. And it too can revolve around the Sun. How many Earth days does it take Mars to make one revolution around the Sun? So we need to use Kepler's laws to figure this out. His third law states that the ratio of the squares of the periods of any two planets revolving about the Sun is equal to the ratio of the cubes of their mean distances from the suns. So basically, this equation, T1 over T2 raised to the second power, that's the ratio of the square of the periods of the two planets, is equal to R1 over R2 raised to the third power. And it makes sense because Mars Mars is further away from the sun. So the distance, the orbital radius of Mars is significantly larger than Earth. So Mars should take a longer time to revolve around the sun. So the period should be significantly greater than that of Earth. So now let's use subscripts to represent Earth and Mars. So our goal is to find the period of Mars in days. So instead of writing T1, we're going to write Tm for Mars, Te for Earth, Rm for Mars, that's the orbital radius of Mars around the sun, or that's basically the distance between Mars and the sun, and then Re, the distance between Earth and the sun. So we're looking for Tm. The period of the Earth in days is 365. It takes 365 days, or 1 year, for the Earth to revolve around the sun. The distance between Mars and the sun is 2.28 times 10 to the 11, and the distance between the Earth and the sun is 1.5 times 10 to the 11. So we can get rid of the 10 to the 11. Those two things, they cancel. So 2.28 divided by 1.5, that's 1.52, and let's raise that to the third power. So the right side of the equation is 3.51181. T squared is just T squared, and 365 squared, that's 133,225. So let's cross multiply. So 1 times T squared is T squared, and 133,225 times 3.51181, that's about 467,860.887. So now let's take the square root of both sides so that we can calculate the period of Mars around the sun. So the answer is about 684 Earth days. So that's 1 year on planet Mars. That's how long it takes for Mars to revolve around the sun. Go ahead and try this problem. It takes Mercury 88 Earth days to revolve around the sun. How far is Mercury from the sun? And we have the Earth-Sun distance. So this time we need to solve for R. So T for Mercury divided by the period of the Earth squared. This is going to be equal to the radius, or the distance between Mercury and the sun, divided by the distance between Earth and the sun, raised to the third power. So Tm, that's 88. That's the time it takes Mercury to revolve around the sun. And for the Earth, it's 365 days. Re, that's going to be 1.5 times 10 to the 11. And we're going to raise that to the third power. And then we need to solve for this variable. So let's cross multiply. So what we have is 1.5 times 10 to the 11 raised to the third times 88 squared, which equals 365 squared times R cubed if we cross multiply. So 1.5 times 10 to the 11 raised to the third power, that's 3.375 times 10 to the 33. If you multiply that by 88 squared, you get 2.6136 times 10 to the 37, and then divide that by 365 squared. So what we now have is R to the third is equal to 1.962 times 10 to the 32. So at this point, we could take the cube root of both sides. If you can't find the cube root function, raise both sides to the 1/3. So then you get a distance of 5.8 times 10 to the 10 meters. So that's the distance between Mercury and the Sun. Now let's go over the elevator problem. So let's say a person is in an elevator and they're standing on a scale. What will the scale read if the elevator is at rest? So if the elevator is not moving at all, the scale is going to read the weight of the person, which is simply mg. So that's going to be 50 times 9.8. And that's going to be 490 newtons. So that's the answer for part A. Now what about part B? When it's moving upward at a constant velocity, what will the scale read? Now imagine if you're in an elevator. When do you feel that unusual feeling in an elevator? Is it when the elevator begins to accelerate upward, or while it's moving, or while it's about to stop? You can feel the acceleration, you can feel a different weight force when the elevator begins to accelerate upward, or if it begins to accelerate downward, or if it's moving up as it begins to, just when it's about to stop, you feel it. But while it's moving up at a constant speed, or if it's moving down at a constant speed, you don't feel a thing. That's because the normal force of the floor inside the elevator, it doesn't change at constant speed or if the elevator is at rest. Only when the elevator accelerates upward or downward does the normal force change. And you feel that effect in the elevator. So the answer for part B and part C is simply 490. The normal force exerted on you by the ground will be equal to the weight force, regardless if the elevator is at rest or if it's moving at constant speed. Now what happens when it accelerates upward? Will the scale read a force that's greater than the weight force or less? The scale is going to read the normal force that it exerts on you. The normal force is an upward force. The weight force is a downward force. So if the elevator is accelerating upward, the normal force has to exert a force to support your weight, plus it has to lift you upward. So it has to be greater than the weight. It takes more effort to support not only the weight of the object, but also to lift it to a higher position. The net force, therefore, is the difference between the normal force and the weight force. The net force, according to Newton's second law, is mass times acceleration. The weight force is mg. So if we add mg to both sides, we will get this equation. ma plus mg is equal to the normal force. So if we take out the mass, we can see that the normal force is dependent on acceleration. So as the elevator accelerates upward, the normal force is going to be 50 times the upward acceleration of positive 2 plus the gravitational acceleration. So it's going to be 11.8 times 50. So the scale is going to read a normal force of 590 newtons. Now let's calculate the normal force as the elevator accelerates downward. So the normal force is going to be 50 times an acceleration of -5 plus the gravitational acceleration of 9.8. So 9.8 minus 5, that's 4.8. So 50 times 4.8 is 240 newtons. So as it accelerates downward, the scale is going to read a normal force that's less than the weight force.